Hi friends, recently I made a video on power system transients based upon the topic how the wave starts traveling from one side to another side through the transmission line, through electrical power transmission line. So based upon that I made a video. So before seeing this video, I request you please go through the video to understand this. Now I am just doing the second part of my video lectures on power system transients. Here in power system transient, there we treat the voltages as well as the currents as the traveling waves. And if you observe, the voltage wave that starts traveling from, let us take this as sending end and this as receiving end, for example. So one wave starts traveling from sending end to receiving end. Through the line, it will see some impedance, and exactly at the receiving end, the wave is experiencing the change in impedance. Means here the load impedance will be some value and the line impedance will be some other value. We don't know them. So usually if the impedances of the line and the load here which is connected are of different values, automatically this signal which is moving from sending end to receiving end will experience a change in impedance. When it is experiencing a change in impedance, you will have the voltage, this is the thing but the incident voltage. From this voltage, two voltages will be divided. One is the reflected voltage, and this voltage comes back from receiving end to sending end, and you will have another voltage which is appeared at the receiving end. So you will have two voltages. So this voltage, which is the incident voltage, is divided into two different voltages. One is the reflected voltage and another one is the transmitted voltage. Hence we call the voltage, this one, as incident voltage V. Similarly the current I as the incident current. This is my way of taking the symbols for different voltages. If you observe, this is the incident voltage V and this is the incident current I. Similarly, this V dash is the reflected voltage and the I dash is the reflected current. V double dash is the transmitted voltage or the refracted voltage, and I double dash is the refracted current or transmitted current. So by seeing this, we can understand from the basics that the voltage which is incident from one side to another side must be equal to sum of the transmitted voltage here is the sum of two different voltages. V double dash is equal to V plus V dash. So this is the condition that we need to know. Similarly for currents, I double dash is equal to I plus I dash. So I double dash is equal to I plus I dash and V double dash is equal to V plus V dash. So these are the voltages and currents for transients. So now we will see in order to understand the different terminations in the sense with which element, either it may be a resistance, either it may be inductance, either it may be capacitance, or maybe open circuit or short circuit. These are the elements that the line is terminated by. Hence, in order to understand the behavior of the transmission line for different transient conditions, means for different line terminations, we need to understand one basic case study, one basic fundamental thing. That basic fundamental thing here is, first we need to take the line, this is the line, and let us assume the line impedance as ZS, and understand that this line is terminated by load. Assume that the load impedance is ZL. So here ZL is nothing but the load impedance, ZS is nothing but the surge impedance of the line. Now it is the case where the line is terminated by an impedance whose value is not equal to surge impedance of the line. Now we can see different situations like this. Those different situations are, one is when the line is terminated by inductor, and the second situation is when the line is terminated by a capacitor, and the third situation is the line is terminated by open circuit, and the fourth situation is when the line is terminated by short circuit. If you observe, when the line is terminated by inductor, the inductor reactance, which is the load impedance, is not equal to surge impedance of the line. When the line is terminated by a capacitance, here also the capacitive reactance, the impedance of the capacitance, is not equal to surge impedance of the line. And if you see the open circuit load has the infinite impedance. The impedance of the load is infinite and the line impedance is finite, so these are also not equal. And in the short circuit case, the impedance is 0, but it has a finite impedance of ZS. In all these cases, we can see that the load impedance value is not equal to surge impedance of the line. If we understand this case study, we can understand all the remaining 4 easily. So that is the reason why first we need to know the basic case study where the line is terminated by a load whose impedance is not equal to surge impedance of the line. Now we will understand with the help of some coefficients related to the transients. These coefficients are called, one is the, we will see now. So first we will understand the first coefficient. That first coefficient is transmission coefficient. Transmission coefficient. So transmission coefficient is basically the ratio of transmitted voltage to the incident voltage, or it may be the transmitted current to the incident current. So we have 2 types of transmission coefficients. One is for voltage and another one is for current. So I just give the symbol for this coefficient, which is TV. TV is nothing but the transmission coefficient for voltage. It is nothing but the ratio of transmitted voltage to the incident voltage. And I'll give another symbol for this. This is TI. TI is nothing but the transmission coefficient for currents. It is nothing but the ratio of transmitted current to the incident current, or refracted current to the incident current. So this is the transmission coefficient, and we will see another coefficient, which is the reflection coefficient. Reflection coefficient. So reflection coefficient can be defined simply as the ratio of reflected voltage to the incident voltage, or ratio of reflected current to the incident current. We can understand like this. As it is for voltage and as it is for current, I can give the symbol for this is as RV. RV is nothing but reflection coefficient. V indicates it is the reflection coefficient for voltage simply, and this is RI. RI is nothing but also reflection coefficient, and it is for currents. So all these coefficients, TV, TI, RV and RI has no units, because they are the ratios of 2 similar quantities. This is the ratio of 2 voltages, 2 currents. Again it is the ratio of 2 voltages. This is the ratio of 2 currents. Hence they don't have any unit. They just give what is the percentage of the transmitted voltage out of the incident voltage. What is meant by this? out of 10 kilovolts, for example, that I supplied from sending end to receiving end, how much is appeared across the load, how much the load accepted, and how much the remaining comes back. So in this way we can understand the transmission coefficients and reflection coefficients. Now we will see that determination of these coefficients for the case study where the line impedance is not equal to surge impedance of the line. The load impedance is not equal to surge impedance of the line. So in order to understand that, first I am taking a line and it is terminated by an impedance like this. So this is the surge impedance ZS and this is the load impedance ZL. Here the situation is the ZL is not equal to ZS, and we already know that this is the sending end side, hence I am assuming this voltage as a sending end voltage, and this is the sending end current. You will have a receiving end voltage and receiving end current. As I am transmitting the voltage from this side to this side, this voltage is called the incident voltage. I am assuming this as V. Some voltage will get reflected back, as we have seen earlier. That voltage is V dash. So V, which is the incident voltage, moves from sending end to receiving end, whereas V dash, which is the reflected voltage, moves from receiving end to sending end. And you will have some voltage which is appeared across the load. That voltage is V double dash. Now we need to understand two relations in order to solve this. So the two relations are V double dash is equal to V plus V dash, and I double dash is equal to I plus I dash. So we need to know these two relations in order to solve this and to determine different coefficients. So in order to do that, first I am taking the help of this equation, which is I double dash is equal to I plus I dash, and we know that the relation between the currents and voltages in a transmission line is like this. I double dash is the refracted current or the transmitted current, so it can be written as V double dash by, where this voltage will appear at the load side, hence it is V double dash by ZL, and it is equal to I, which is the incident current. The incident current is again the ratio of incident voltage to the impedance of the line, surge impedance of the line, which is ZS. And I dash, this is just different when compared to these two. Here I dash is related by like this. It is minus V dash divided by ZS. So these are the relations between the currents and voltages in a transmission network. So from this relation we can solve this in this way. V double dash by ZL is equal to V by ZS minus, in place of V dash, from this equation I can substitute V double dash minus V. So here I will get V double dash minus V by ZS again. So from this equation I will get V by ZS minus of V double dash by ZS minus of minus plus V by ZS, and it is V double dash by ZL. If you send V double dash terms to one side and V terms to other side, you will get V double dash 1 by ZL, and if you send this to here, it is 1 by ZS. It is equal to V by ZS plus V by ZS. It is 2 times V by ZS. Now just I am erasing this portion as I am out of space here. So from this equation I can write V double dash into, by taking LCM you will get ZL into ZS, and in the numerator ZS plus ZL is equal to 2V by ZS. So ZS gets cancelled, and you will have, I am just sending this V to here and this denominator to here, so that I will get V double dash by V is equal to 2 into, if I send ZL here, I will get ZL plus ZS. So what is V double dash by V? We already gave the definition of V double dash by V. It is the transmission coefficient for voltage, which is TV. So TV is equal to V double dash by V is equal to 2 ZL by ZL plus ZS. So this is the equation for transmission coefficient, and like that you can derive the remaining things like this. This is the equation for transmission coefficient for voltages. Okay, if I want to define for transmission coefficient for reflection coefficient for voltage, I can write this as RV is equal to V dash by V, and so I can have here in place of so we must know the relation between first RV and TV to get TV. So actually RV TV in place of V double dash. So actually I can write V plus V dash by V, so that I will give it like this: V by V plus means 1 plus V dash by V. V dash by V is RV, so TV is nothing but 1 plus RV. So from this I can find RV value, which is nothing but TV minus 1. So TV minus 1 is this one, TV is this one. So 2 ZL by ZL plus ZS minus 1 will gives us 2 ZL, and 1 ZL will get cancelled. You will get ZL minus ZS divided by ZL plus ZS. So these are the transmission coefficients and reflection coefficients. So when the line of surge impedance ZS is terminated by, when the line of surge impedance ZS is terminated by ZL like this, when the line of impedance ZS, if it is terminated by impedance ZL, I will get the coefficients as TV is equal to 2 times ZL by ZL plus ZS, and RV is equal to ZL minus ZS by ZL plus ZS. If I want to just apply this rule for open circuit condition where this ZL is infinite, here from TV just I can take ZL as common from the denominator. So ZL, if you take ZL as common, you will get ZL into ZS by ZL. So ZL get cancelled. 2 divided by 1 plus, what is ZL value? 0. 1 plus something by infinity is 0. So we will get TV. What is the meaning for that? V double dash is equal to 2 times V. So under steady state condition, you will have a refracted voltage 2 times the incident voltage if the line is terminated by open circuit. And we will see, and we will apply this concept also to the open circuit. So RV is equal to, by taking ZL as common from the numerator and denominator, you will get 1 minus ZS by ZL divided by, so this is ZL common, and this is also ZL common in the denominator, 1 plus ZS by ZL. So ZL gets cancelled. You will get 1 minus ZS by ZL by 1 plus ZS by ZL. As ZL is infinite, this term is 0 and this term is 0. RV is equal to 1, which indicates that V dash by V is equal to 1. That implies V dash is equal to V. So when the line is terminated by open circuit, there is a reflection of the same voltage. Whatever the voltage which is incident from the sending end, that voltage again will be reflected back from the receiving end. In this way we can apply these two concepts. Now these are the concepts for voltages. Similarly for currents we can derive Pi and Ri. From these four coefficients we can understand the nature of how the voltage is reflecting and how the voltage is transmitting at the load side for different load terminations. Okay, so in order to understand this, first we need to understand a basic case study. That case study is when Zs is not equal to Zl. If you understand this, you can understand open circuit, short circuit, inductive load, capacitive load in a comparatively easy manner. So hope you got some idea about the different coefficients related to the wave traveling in power system transients. Thank you very much. And if you like this video, or if you like any video which is made by me, I request you please subscribe to my YouTube channel. Thank you very much.